Hello and welcome again with the IB chemistry exam HL happening on Friday this week. I wanted to continue my tips by focusing now on HL tips given by the examiners based on the performance of students in last November's examination. And these are 4 major points that came out of that exam, and they're listed here for you. So let's move straight in and take a closer look. And here you can see that students did find some difficulty with this particular topic, the depletion of ozone by chlorine-free radicals. Ozone is constantly being broken down or depleted in the stratosphere in the presence of ultraviolet radiation. O3 going to form O2 and an oxygen-free radical. And then the reverse process happens, and ozone constantly breaks down and reforms, and this is how it protects the Earth from harmful ultraviolet rays which come from the sun, but in the presence of chlorine-free radicals. Now these chlorine-free radicals find their way up into the stratosphere through a series of steps which are not going to be covered right now. But once chlorine is up there in the stratosphere, in the presence of ultraviolet light, it too can break into 2 free radicals, a chlorine atom in other words. And here you have an example of what is called a homolytic fission. So with this homolytic fission and this highly reactive chlorine-free radical being formed, then it goes in and begins its cycle of ozone depletion. Cl free radical reacting with O3 to form this species here. And then this species goes on to mop up another one of these important free radicals of oxygen to form O2. And then most significantly, a free radical is regenerated to go back and carry out this process over and over again. And what that means is that oxygen-free radicals and ozone molecules are being depleted from the stratosphere, and we are just getting a buildup of O2. This entire important equilibrium that protects the Earth gets broken up, and in this way we say that ozone depletion happens through these 2 steps. This equation here was also accepted by the examiners. And now we come to this question. Determine the frequency of a photon that will cause the first ionization energy of copper. And the problem that occurred with this particular question really came from knowing what a photon was, because a photon deals with the energy associated with a single electron. A photon is produced whenever an electron in a higher than normal orbit falls back to its normal orbit, or any single electron that's undergoing a transition. The energy that's associated with that single electron is defined as a photon. So with that in mind, we could then go into section 1 of the data booklet and recall this equation. E energy equals H Planck's constant multiplied by nu, the frequency. We should also recall that the Avogadro's constant, 6.02 by 10 to the power of 23 of any entity, making up that 1 mole. And the first ionization energy of copper given in section 8 of the data booklet, given here as 745 kilojoules per mole, also could be expressed as 745,000 joules per mole. Planck's constant is given in joules second. So with all of this relevant data on this side, we can move over to solving and answering this particular question. First up, we need to take this value here, which is per mole. We don't need all of 1 mole of the copper. We simply need 1 copper atom. And 1 copper atom is going to be 745,000 divided by 6.02 by 10 to the power of 23. And once we solve for that, we would end up with 1.24 by 10 to the negative 18 joules, that being the energy associated with the single photon. That energy, of course, is not the frequency. Then we look at this equation, E equals h nu. We get Planck's constant here from the data booklet, and we plug it into this equation, and then we realize that we need to solve for nu, the frequency. And then when we go with E divided by h, Planck's constant, and we solve, we get 1.87 by 10 to the minus 15 per second. But of course, that is better expressed as 1.87 by 10 to the power of 15 hertz. And our last topic, ethanoic acid is titrated using potassium hydroxide, and the pH curve for the reaction is given here. The first thing that you had to do was to write the balanced equation for this reaction. So ethanoic acid, potassium hydroxide, the salt of potassium hydroxide and ethanoic acid, and water. Acid plus base gives salt and water. Then, the part that proved difficult for students was the second part of this question here. At B and C, what species are found other than water and K+? Now, what students need to recall is that this is your buffer region, and it exists when you have a titration happening between something like ethanoic acid, a weak acid, and something like potassium hydroxide, a strong base. A similar kind of buffer region could exist if you have the reverse, which is a strong acid and a weak base. But in this particular case, as ethanoic acid begins to get consumed and it's halfway through its consumption, like somewhere around here, that is the buffer region. And that buffer region, there is an equilibrium between the weak acid and its conjugate base, as shown here. And both are in equal concentrations at that point. Beyond the buffering region, like region C, that is where the acid is completely consumed, and you then have the conjugate base in high concentrations and the acid completely consumed, and this is where you then have the neutralization happening and the huge change in pH. So the answer to this question then would be, at the buffer region you have these two species at B, and at C here you have this species present. Also useful to recall that at this buffering region you do have an equilibrium existing, like this one here. When this equilibrium exists, we could say that Ka for this weak acid could be expressed like this. And then we should also realize that if these two entities are equal, then Ka ends up being equal to H+. And if Ka is equal to H+, we should also be able to say that pKa, the negative log to the base 10 of Ka, is equal to pH, the negative log to the base 10 of H+. So with pKa being equal to pH at B, we should also know that that is another important point to note for questions, and it's also important in helping us to select the buffer and helping us to select the appropriate indicator for use in this titration.